Why is my video not showing? Oh, there we go. Okay.
Hi, Adrian.
Hello.
We'll be getting started in about 4 minutes, so if you want to go get something to eat or drink or whatever, that's fine.
Okay.
We'll be getting started in about 2 minutes. If you want to get something to eat, something to drink, that's fine. We'll get started here in a second. So you guys doing anything interesting? Oh, Morgan, I like your, or no, Tessa, that's Tessa. I like your background. That's pretty cool. Have you guys ever gone to Chain Lakes State Park? No? It's kind of nice if you're getting claustrophobic or anything. It's a short drive away from here, and there's not that many people there. It's kind of out in the country, so I definitely recommend it. If I kind of like going out in the woods, it's quiet and everything, so it's really nice. Okay, I think we're going to go ahead and get started. So I kind of want to just refresh your memory of the labs that we started to whiteboard last week, and then we'll finish them up today. The goal is that you'll know all the answers for the lab response. That way you can go ahead and turn in your lab response for homework. That's going to be due before the next Zoom meeting, which will be on Wednesday. So anytime between now and Wednesday, you can turn it in. As far as how to turn it in, there are two ways that you can do that. Either for the people who maybe have a paper version, maybe you printed it out something. If you like more having the paper version, you just writing it by hand and you've already got it done and you just want to send me pictures of it, you can do that. Or if you're like, well, I've done all the work on the whiteboards, can I just turn that in? That's that's fine, but I need to know who you're saying gets credit for it. You know, that means they participated. And so just make sure, Nate, all the names are on those whiteboards of who's getting credit for that. And please put all the whiteboards for a particular lab in one folder. Don't send me a whole bunch of links. Just send me the one link for the one folder for the lab. That's fine too. You could do whatever way is easier. That's fine. Okay, so I think I'm going to go ahead and get started. So let me share my screen with you. Okay, so if I can get, there we go. All right, so for the explosion lab, we already looked at the graphical models. I don't have them up here, but you should have it. I don't think I have it on here anyway. I deleted it out of there. Maybe I can go to a prior version. I'm not sure. Nope, I can't. Okay, that's all right. But the relationship we found was kind of a negative inverse relationship. And so when you linearized it, it kind of looked like this. The mass of the red times the velocity of the red, getting rid of the fractions, equals the negative mass of the blue times the velocity of the blue. And what we did was we defined this new quantity that we called momentum. Momentum, we're using the letter P for that, is equal to the mass of the object times the velocity of the object. Since the velocity is a vector, momentum is also a vector. So I didn't put the vector symbols on there. Didn't really have time to do that. But anyway, so momentum's a vector because velocity is a vector. So I kind of wanted to go over the answers for 17 through 20 together. I don't really think we need to whiteboard them. I think we just kind of talk about it. So if you remember, I probably need to remind you what this lab kind of looked like. Was you had this track and you had two cars on the track, a red one and a blue one. And there was some way that they kind of shot away from one another. So some kind of like a spring between them or something. And so the red one kind of shot off one direction, the blue one kind of shot off another direction. Okay, so the question is this. If both cars had exactly the same mass, so let's say the mass is M, and they both have that exact same mass, and you triggered them and they shot away from one another, how would their velocities compare? How would you expect their velocities to compare? So how about you just unmute yourself and say, what do you guys think?
It'd be the same.
Same speed, right? But
Yeah.
remember, velocity is a vector and they're kind of in opposite directions. So same speed, but opposite direction, right? Yeah, okay. All good? Everybody good? Okay. All right. And what's the reason why? That's kind of more important. Why do you think, I don't know, something's going wrong with my, let's try that again. I'm trying to circle the word why. Dang it. There we go. So what do you think that is? Anybody, just shout it out. Why do you think they have the same speed, opposite direction?
Would it perhaps have something to do with Newton's third law of motion?
It's similar, right? Does it kind of remind you that? So in other words, if you're thinking about it, they should have the same magnitude force on them because it's a spring acting between them, and they have the exact same mass on them, or I should say they have the same inertia, so the same laziness factor. So I think it kind of makes sense that if they have the same force, same inertia, that after the force gets done acting, they should have the same speeds kinematically. So yeah, I think that makes sense. In past years, we've actually been able to do this lab in class. And it turns out that a lot of times they don't really have, so when you really do this lab in class, real situations, it turns out that the velocities aren't the same. So let's say the speed is, or I shouldn't say the same, equal and opposite. Let's say the speed of the blue one is a little bit less. Can you think of any real world reasons why it might not be the same?
If they started at different initial velocities.
So like, yeah, if the whole thing, let's say the whole thing was kind of moving, they were stuck together and they were moving in one direction. Yeah, that's a possibility. Other ideas. So maybe they had some initial, maybe there's friction, right? So maybe friction acts on the blue car more than on the red car. So maybe they have initial velocity, maybe there's some friction. Any other ideas?
If like there's wind blowing in one way, so there's air resistance in a certain direction.
I think if he was outside, that's probably true, but in the lab, that isn't usually a problem.
Mm.
Any other ideas?
Maybe the explosion is not directly in the center.
Oh, okay. So in other words, it's not able to push exactly in the direction of the track or something like that.
Mm-hmm.
It's kind of nice that the mechanism in class, unfortunately, you guys aren't going to be able to play around with it. The mechanism in the class is actually inside one of the cards. So it actually is right along the line of it. But a lot of times so it should be right in the same direction. What I was thinking of, something that happens more likely in the class. So some people have, so you guys said friction, that's a good one. There might be an initial velocity in class, you're right, it might be rolling a little bit. A bigger one is that it might be having an angle to the ramp, it might be tilted a little bit. And that happens a lot in class, that you have to kind of adjust it. So the big ones are, there's a ramp that has, the ramp is a little bit tilted, and the other one is that there's a little bit of friction usually. That's the big ones. Okay. Let's go on to the next question. Close out. Okay, so for the next one, let's say we're thinking about a gun exploding. So let's see if I can find the image of the gun. So cartoon gun. Gun and bullet. There we go. Maybe. Okay, so here we have this bullet that's being shot out of this gun. In this situation, we have the gun kind of moving in one direction. Can you guys hear a beeping in the background? Oh, okay. I can't get this thing to grab. So we have the bullet moving in one direction, and we have the gun moving in the opposite direction. But the bullet speed is so much faster than the gun speed. So the question is asking, why is it that the bullet acquires a greater speed than the gun?
It was a smaller mass.
Because it has a smaller mass, right? Yeah, that kind of makes sense. So I have a question. What if, instead of this bullet here, what if I had a bullet that had a much bigger mass to it? Let's say that's the bullet being shot out. And let's say it has exactly the same mass as the gun. How would its speed compare to the speed of the gun? We call this a recoil velocity for the gun. How would its speed compare to the recoil speed of the gun?
Equal.
Yeah, it'd be the same. Yeah. So that's probably not a good design in a gun and bullet. You probably don't want it to be the same mass. You end up, I guess, shooting your own arm off. I don't know. Okay, that'd be a bad idea. All right, so next question. All right, so let me get rid of that. Number 20. Number 20, actually, I don't actually want you to do that one because, I mean, since you weren't able to do the class lab, it doesn't even really make sense. So just strike that one off. So your lab response, you don't need to do that one at all. Okay, so we're done with the explosion lab. So let's move to the impulse lab. So the impulse lab, let's look at the graphical relationships. For this one, again, I didn't save it, but what we had was a direct relationship. And so the relationship we said was the impulse, J, is equal to the change in momentum. So mvf minus mvi. When it's a constant force, the impulse would be force times time, and that would be equal to that change in momentum. So mvf minus mvi. And that's what you're going to be using, that mathematical model for these. So how about I give you a few minutes to do 15 through 19. Those are true, false, okay? So give you a few minutes to work on those. So I'm going to stop sharing and let you guys work on those. Okay, what I would like to do is I would actually like to try to make this like whiteboarding in class. So at the very bottom of your screen is a share button. It says green, it says share. If you click on that, you don't have to do that right now, but when you click on that, then a pop-up will come up and you'll just click the blue share. And I'm just wondering if somebody would be willing to share their whiteboard with us. The quicker we get it whiteboarded, the quicker we're done. That's your incentive. So whoever wants a whiteboard and share the whiteboard, go ahead and you can take control, share your screen. Yeah, thanks, Alyssa. Okay, so Alyssa, can you talk? Maybe hit the F4 key and unmute yourself, or excuse me, the F1, F4, I think. Oh, there you go. There you go. So for the first one, number 15, you said momentum is a vector quantity. You said true. Okay.
Yeah.
So yeah, I think that makes sense. We have velocity has its momentum's mass times velocity, so it has direction. So yeah, that makes sense. All right. Change in momentum is a scalar quantity. Change in momentum is also called impulse. So yeah, I think that makes sense. It would be a vector quantity. So that doesn't, okay. And Alyssa, for that next one, that integration
Is that
symbol,
like the integral for the
Right.
force distance? Wait, no, dt is just the thing that you put on the end of it.
yeah, so you're wanting to look at the integral, and really what that is impulse. It's the same, actually 16 and 17 are kind of like the same thing. Impulse is a change in momentum, and that's just another way of writing
Okay.
it. So I
Yeah.
agree, that makes sense. It would be false.
And so the integral of it wouldn't be the same thing as momentum, but it'd be the change in momentum.
There you go. Right. So that one's false too. And then the last one is equal to change momentum. Nice. Any questions? Everybody good? Thumbs up? Yeah. All good? Thumbs up? Okay. All right. I'm going to take control. Thank you very much, Alyssa. All right. So then the next one we're going to whiteboard is number 20. And my suggestion is for this one that you use that mathematical model that I kind of showed you over here, that F times T, the impulse, is equal to MVF minus MVI. So kind of use that one to solve that one. So how about I give you 2 or 3 minutes to work on number 20, okay? I'm gonna stop sharing.
Hi.
Hi.
Sorry.
Oh,
Something
that's fine.
like went weird with my internet, so it
Yeah,
just
no problem.
shut me out. I was like, oh no.
We're still working on number 20.
Okay.
Anybody want to share their whiteboard? Somebody different? Again, it's just the bottom. You click on the green share button at the bottom, and then you hit the blue share button. Morgan, thank you.
Okay, so I basically just said like the interval or integral of the force times time graph, or like F times T equals change in momentum.
Okay.
So then the change in momentum would be the final momentum minus the initial momentum. And you can do that by doing like the mass times velocity minus the mass times velocity. And then I got -15 with those units.
Perfect. Yeah. The only thing I'm going to change is so your math is absolutely perfect. But at the very end, notice how it says it's to the right. And so your final answer after doing all the math is absolutely perfect. Your final answer, you would just say 15 kilograms times meters per second to the left. That's
Okay.
it. Yep. Any questions? Okay, so I'm going to share my screen again then. Okay, so that one's done, and now we're getting ready to do number 21. 21 kind of goes along with number 20, but this time we're trying to find the force. So now you know what the impulse is. You found that number 20, you found the impulse. And so now you're just trying to figure out the force given that the time is 0.1 seconds. So how about I give you another couple minutes to do that one, and then we'll share that one. Does anybody want to go ahead and share their whiteboard? A different person. Keep in mind, it's just like whiteboarding. If it's not right in class for a lab, if it's not right, it's no big deal, right? You're not getting graded on this. You're going to turn in your correct lab response afterwards. So I think this is Josie. Josie, can you go ahead and maybe unmute yourself and Uh,
Okay.
okay, and then,
So,
yeah.
so 15, that was the change in momentum. So then you just do that times the force times the time. So then you can just divide easily.
Okay,
So
and perfect. The only thing I would add is that we need a direction because it's a vector quantity. And since the change in momentum was to the left, if you remember, Morgan got a negative, so that meant to the left. That means this force is also to the left. So, any questions? All good? Everybody's good? Thumbs up? Yeah? Okay. All right, I'm going to go ahead take the screen back. Okay. And so we're done with that one. Let's go ahead and whiteboard 22. 22, it's a similar idea. It doesn't go along with the other two problems, but you're going to use the equation that we have here. Impulse, force times time, is equal to MVF minus MVI. So if you can go ahead and whiteboard number 22, I'll give you a few minutes to do that. Anybody want to share their whiteboard with us? A new person, hopefully. Katie. Okay, Katie, can you unmute yourself and tell us what you did?
Yeah, so like we learned that the MVI minus MVF equals force times time. So it started from rest, so I did 0 minus m, and then we don't know the final velocity equals the force times the time, and then if you divide it out, you get negative 4.8, which is the same thing as 4.8 to the left.
Okay, so so your answer is totally right. The only
Okay.
thing I would say is it's actually MVF minus MVI.
Oh, okay.
And since it says it's 20 Newton force to the left, that's where that negative came from. So it would have been a
Okay.
negative 20 times 1.2. But your answer is totally right. 4.8 meters per second to the left.
Okay. Thank
Any
you.
questions? Good. Everybody good? Good? Okay. All right. So I'm going to go ahead and take control again. All right. So, and then number 23. Kind of a similar problem for this one. And again, the equation is the impulse, force times time, is equal to MVF minus MVI. So how about I give you another couple minutes to do that problem? Anybody want to share their whiteboard? Somebody different, hopefully. Calvin, okay. And Calvin, if you can unmute yourself and kind of
Yeah.
walk us through. Okay.
Yeah, so impulse equals MVF minus MVI, and M is 1.5, and it goes from 10 to negative 10. So it's negative 20 times 1.5 is negative 30.
Perfect. So I want to talk about this one a little bit. I'm going to go ahead and take control back.
Yeah.
So I think you did that perfect. So this is one of the problems that, kind of a conceptual problem that sometimes students have a hard time with, because usually when you think of something moving along here, let's say this is a cart and it's moving toward, let's say, a spring. I don't know if I can even draw a spring. How do I draw that? I don't know. So, okay, so let's say this is a spring here. It's coming toward this wall. And, oh, come on. And so it's going to hit the wall, and then it's going to bounce off the wall. So at first it's moving this direction, but then it's going to hit the spring, kind of bounce off of it. So we usually think of this as kind of a nice, you know, cushion thing, almost like with a bumper on a car, right? And it's bouncing off of it. And we usually think of this as being kind of a gentle thing. But really what we're seeing here is, and in fact, I'm going to kind of show it here. Let's say you have two cases. You could have the case where the car is just going to hit the wall and come to an abrupt stop. That would be a force times time would be equal to MVF minus MVI. MVF would be 0. So it's going to be 0 minus mass times the initial velocity. And so we get some value. But in this case, where it bounces off, we have force times time equals mass times, let's say, negative 10, because it's going in the opposite direction, minus mass times positive 10. And we actually get a bigger number here. So the point of this is that when you have something that's bouncing, we actually get a bigger impulse, which is kind of strange because usually we think of it being smaller. And the reason why students get this wrong a lot of times is because they forget this is a vector and they'll leave off the negative here and they'll see, oh, it's 0. And that's not correct. It's actually going in the opposite direction. So it's actually a bigger impulse. And that kind of leads me to my next problem, actually the last one, I think, right? 24. It's not loading. There we go. And I think I just want to answer this one together. So Johnny says that bumper cars are safe because the impulse, that would be the integral of f dt, the impulse experienced by an occupant is less than that experienced by someone just hitting an object and coming to a stop. In other words, it's safer to bounce because the impulse is less. What do you guys think? Is Johnny right?
No.
No, he's not right. No, he's not right. So what is the mistake that Johnny's making there to think the impulse would actually be less? So let me, oops, where was it at? Sorry, 23. Let me go back to this one here. See if I can copy. So I think this is the mistake that Johnny's making. He's thinking you have some speed coming in and you have the same speed going out. And so when you subtract these two, you end up getting 0. And I think that's what Johnny's thinking. He's thinking this is equal to 0. But that's not true because Johnny forgot it's actually a vector. And so you're actually going to be adding, it's going to be a bigger impulse. Does that make sense? We all good? Yeah, okay. It's a bigger impulse. All right, so now let's talk about, okay, so we've done all this. So I'm going to go back to the calendar real quick. So what that means is you should be able to send me a email with your labs. Again, you could either have a printed out version that you just send me a picture of, but if you do that, that lab's only for you. It's not for everybody else in your group. Okay, it's just yours. If you wanted to, though, you could just simply make a Google file with your whiteboards for each individual lab and send me that link. And you can actually work on that together. So let's say a couple of you did the lab together, you can put both your names on it and maybe look it over, make sure it's got all the right answers, and then send that to me. And again, just make sure I get that by Wednesday's whiteboard meeting, or excuse me, Zoom meeting at I lost it, Wednesday, here we go, 10:55. Okay, the last thing I need to talk about is the quiz for today. It's just kind of over the stuff we just talked about. So I need to give you the code. And here's the code. It's lowercase y-t, uppercase n-c-c, lowercase e-k, hashtag lowercase v. And I think there's only 5 questions on it, and it's similar questions to what we just did. Let me go back to the calendar because I want to talk about Wednesday a little bit. Wednesday we're going to be whiteboarding worksheet 1, and I've already shared with you links to those, because what I try to do, in fact, let's see if I can show you what that looks like. I've made whiteboards already for your class. Like, I try to group you in normal groups that you're normally in. And so your partner should be here. Please don't do everything on the whiteboard, kind of divide and conquer, because I want everybody to be engaged. I want, you know, kind of assign tasks. That way everybody's doing something on the whiteboard. I'm trying to make it just like we were in class as much as possible. In fact, that brings me to my next point. On Friday, I sat in on a lecture at PFW. The professor there was using something called Discord. I'm not sure if you guys know what that is. I don't really know a whole lot about it. But evidently with Discord, you can have verbal chats. So on Wednesday, I want to see if I can get you guys into a classroom that's set up in Discord, so that you could be whiteboarding on this whiteboard with your partner, and you can actually hear them talk, and you could chat with one another verbally while you work on the whiteboard. That's my hope anyway. So if you want to get started working on worksheet 1, you can, but you don't have to. I'm totally okay with you not doing anything on worksheet 1 until Wednesday, because I'm kind of wanting to know if this Discord thing's going to work or not. So any questions? Okay, so just make sure I get copies of that lab then from you. So that's it. So stay safe and see you on Wednesday. Bye.
Thank you.
Don't forget that that SWIC too. Bye. Bye.